So this section is on molecules and moles. We're going to start by just talking about the molecular formula. You're already familiar with molecular formulas because we've talked about it. You've probably since you were a child spoken about water as H2O. That's a molecular formula. Carbon dioxide, dioxide is CO2. Let me just switch these things for a second. Methane is CH4. CH4. Ammonia is NH3. Silicon dioxide, I think this is better known as sand, SiO2. Those are all molecular formulas. And so let me switch back here. And so a molecular formula uses, it's a representation of a molecular compound which consists of the following. Chemical symbols to indicate the types of atoms. So if I go back, here I'm saying water has hydrogen and oxygen in it, right? These letters are the names that appear in the periodic table, the abbreviations that appear in the periodic table. Right? The subscript after the symbols indicate the number of each atom, the number of each type of atom in the molecule. So there are 2 hydrogens for every 1 oxygen, right? A water molecule, a single molecule of water, which is the smallest amount of water you can have, contains 2 hydrogens and 1 oxygen. The smallest amount of carbon dioxide is 1 carbon, 2 oxygens. The smallest amount of methane is 1 carbon, 4 hydrogens, and so on. The subscripts are only used when more than one of a given atom is present. So if there's no subscript, you just assume it's 1. There's 1 nitrogen in an ammonia molecule. There's 1 nitrogen and 3 hydrogens, right, and so on. A structural formula shows the same information, but also shows how the atoms are connected. So these are molecular formulas. These we're looking at here. And so now let's look at structural formulas, if I can get to it. So here's the molecular formula, and these are 3 different variations of the structural formula, right? This is just a sort of standard structural formula. You just draw the carbon with a link to each of the hydrogens. We'll get into more detail on that as we go. Here's a ball and stick formula. So this is a 2D version, right? But this is an actually 3D version. The ball and stick model gives you an indication of where the atoms actually are positioned relative to one another. And finally, the last one is a space-filling model, which gives you a better idea of how the electrons are living around this model, right? This just tells you the relative orientations. This gives you a better idea of what the cloud of electrons are doing as they're living around this, well, maybe not living, as they're swirling around these nuclei. In this case, the carbon and hydrogen atoms are represented by black and white spheres, respectively. So a molecular formula is just the letters, the abbreviations and the numbers. This gives you a little more information. This gives you more information still, and finally this one gives you even more information. You could go on from there. Many elements consist of discrete individual atoms. So if you're looking for just an element of the periodic table, like how do you find hydrogen in nature, or how do you find nitrogen in nature, or how do you find helium in nature? Very often they just exist as individual atoms, iron atom floating around or something like that. Often they exist as molecules in pairs. If you find hydrogen just floating around in the air, it's in the H2 form almost always. Same thing with nitrogen. Our atmosphere is composed of mostly of hydrogen, nitrogen and oxygen in this form, N2 and O2. In fact, you can occasionally find O3 called ozone, and it's usually in the atmosphere. It's often in the atmosphere, at least near the ground, because of pollution. Humans can't breathe O3, or at least they can't aspirate, respire it. We can't metabolize O3. We can only metabolize O2, and so O3 is kind of a toxin. And when pollution levels are high around cities, they're talking about ozone alerts and things like that. Ozone has another effect in that it keeps UV light when it's out, when it's up in the stratosphere. But that's different. That's a different story. Fluorine appears as F2. Chlorine appears as C2, bromine, and iodine. The most common element of sulfur exists as S8. But often, many atoms will just appear as individuals when they're commonly found. Here's another example of how you might see a sulfur molecule. You could write it as S8. It's typically a ring. And here it is. It's not quite a flat ring. So here is a 3D version of it, right? And this is a 3D version that has a better representation of space filling, how the space is filled. And so those are the different models. So once again, how they're found in nature, you can, if you want to represent a single hydrogen atom, you can just an H. Two individual hydrogen atoms that are not a molecule, you would write it as 2H rather than H2. The H2 implies they're bound together like this, and this would be 2H2. And so keep track of the notation. The notation is telling you sort of how many independent things there are. If you put the number on the left-hand side, this is telling you there are two independent hydrogen atoms. This is telling you there's a single hydrogen molecule with two hydrogen atoms in it. And the last one is telling you there's two individual hydrogen molecules, each with two hydrogens in it. These are all chemically very different. So there are a couple other ways to look at these things. Sometimes, like for example, if you look at the formula for benzene, benzene is C6H6. Hang on a second. Sorry, I made a slight adjustment to that, just to make it a little clearer. The top line here is the molecular formula. So benzene has 6 carbons and 6 hydrogens. The empirical formula just tells you sort of the least common denominator. This kind of tells you there's 1 carbon for every hydrogen. Acetic acid is C2H4O2, and so its empirical formula would be CH2O. That is, say there's 2 hydrogens for every carbon, there's 2 hydrogens for every oxygen, and the carbons and oxygens are 1 to 1, right? And you can see that in the top formula. This is titanium oxide. Sometimes molecules appear, atoms bond in a grid, and so sometimes all that's really interesting is the empirical formula. And so this just tells you that in titanium oxide, the ratio is 2 oxygens for every titanium atom. And you can have as big a molecule as you want, sort of. It just forms a structure that way. Another thing that can happen with molecules is it may be possible for the same atoms to be arranged in different ways. These are called isomers. So I just made a small change there. So isomers are compounds with the same chemical formula but different molecular structures. We saw earlier the pictures of the 3D shape of these molecules that don't appear when you just write the formula this way. But it turns out when molecules interact with others, how they're arranged matters. And so you can have 2 different molecules that have the same chemical formula and they act differently because their shape is different. And so acetic acid and methyl formate both have the same molecular formula, but they have different structure and different properties. So this is acetic acid. You can see it's got 2 carbons, 4 hydrogens, and 2 oxygens. Right? Methyl formate also has 2 carbons, 2 oxygens, and 4 hydrogens. But they have very different structure, and so they act differently. And so we call these isomers. All right. Let's talk about the mole. So the mole is an amount. It's a unit similar the mole is an amount unit similar to familiar units of amounts like a pair or a dozen or a gross, etc. A score, 7 years ago. So the mole is defined as the amount of a substance containing the same number of discrete entities, such as atoms, molecules, ions. It could in fact be anything, cars, buses, planets, and so on. It contains the same amount as the number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. Now the tricky part of this is that this is an enormous number. The mole is an enormous number. The amount of pure carbon-12 atoms weighing exactly 12 grams is this number down here, 6.02214,179 times 10 to the 23rd. That's 23 zeros after it. That's an enormous number. And so you wouldn't ever have that many buses or cars. It's almost always atoms or molecules that you're talking about. In fact, you can't get numbers like this, but then you're talking about how many something are in the universe or something like that. Even then, it's hard to take anything of any significant size. The mole, this number, is a testimony to how small atoms are. That you can have this many atoms in 12 grams of 12 grams is less than half an ounce. So it's a tiny amount of matter, right, of copper, but it has this many atoms in it. It's why it took us so long to figure out that atoms are tiny, that there's a minimum size to matter, right? The mole provides the link between the mass of a sample and the number of atoms or molecules or ions in that sample. The constant is named after the Italian scientist Amedeo Avogadro and is also known as Avogadro's number. We usually write it as 6.02 times 10 to the 23rd or 6.022 times 10 to the 23rd. Again, it's just how many carbon atoms it takes to weigh exactly 12 grams, how many carbon-12 atoms. Okay, so the mass of 1 mole of different atoms, however, is different, right? In the same way that a mole of bricks would weigh something different than a mole of cinder blocks, which would weigh something different than a mole of pebbles. A mole of hydrogen atoms weighs something different, has a different mass than a mole of carbon atoms. So here's some examples of moles. You can look across here and say, this is 65.4 grams of zinc, 12 grams of carbon, 24.3 grams of magnesium, 63.5 grams of copper, and so on down the line, right? So each one of these is a mole. So just as a mole of bricks and a mole of cinder blocks have different masses, a mole of zinc atoms and a mole of carbon atoms have different masses. If you look at a periodic table here, you'll see over here this number below the magnesium, for example, is 24.3. That's the atomic mass of a magnesium atom in atomic mass units. Well, the mole is defined so that for carbon 12, a mole of that is 12 grams. That means a mole of magnesium is going to be 24.3 grams. If you just take the mass in atomic mass units, this number here, and call that grams, that will give you a mole of that entity. And so we said I think we had sulfur here is 32.06. I think copper, it said, was 63.5. It said lead, which is all the way down here somewhere, PB. Help me find PB. Can you get to it before I do? Here it is. Lead is 207. They said, right? Zinc was 65. Here's zinc, 65.4. And so in every one of these cases, you have if you want to have a mole of these, it's this many grams. A single atom weighs that many atomic mass units. A mole of atoms has a mass of that quantity in grams. And so it's pretty easy to remember. So if you want to have a mole of water molecules, you would have to have 2 times the 1.008 grams of hydrogen, because you'd have to have 2 moles of hydrogen, because it's H2O. And then you'd have to have 16 grams of oxygen to get a mole of oxygen. So you would have a mole of water molecules has 2 moles of hydrogen atoms, because there's 2 hydrogen atoms for every water molecule. And so this would be 2.016 would be twice that, plus 16, so it would be 18.016 would be the mass in grams of a mole of water molecules. 18.016 is about half an ounce of water, which is, I don't know, is that a tablespoon or 2? Maybe a tablespoon, something like that. Okay. So you can also do, this is where I was here. And so I came down one screen. The molar mass of an element is just the mass in grams of 1 mole of that substance. And so you just take the mass in atomic mass units and write it in grams. And so a single carbon-12 atom has a mass of 12 atomic mass units. A mole of carbon-12 atoms has a mass of 12 grams. You can extend this to molecules. So each of these samples is a molecular entity, and they're all, it's a mole of each of those molecules. And so, for example, clockwise, it says from the upper left. I think it's this guy. This is 1-octanol. I don't know what that is. But its formula is C8H17OH. And so if we wanted a mole of these molecules, let me just switch to the sheet here for a second. So I wrote those down. Let me just, let's say we wanted a mole of this octanol stuff, right? It's gonna have 8 carbons, right? It's C8H17OH. So it's technically got 8 carbons, it's got 18 hydrogens, and it's got 1 oxygen, right? And so if you go to your periodic table and you look at carbon's atomic mass in atomic mass units, carbon is 12.01. Right, let me just switch back here for a second. Right, carbon is right here, it's 12.01. And so this is 8 times 12.01 plus 18 times 1.008 plus 1 times 16. And when you add all that up, it comes out to 130.2. I think it's 0.224 or something like that. And so, so you get an atomic mass. Let me just go back to that. Oh, there we go. Right, for this molecule, you're going to have in every molecule, you're going to have 8 carbons, 18 hydrogens, and this is oxygen. So this is 1 oxygen. this is an O, not a 0, right? Carbon, hydrogen, oxygen. And so it's going to be 12 times the molar mass of carbon, 8 times the molar mass of carbon, 18 times the molar mass of hydrogen, 1 times the molar mass of oxygen. Multiply all that stuff, add it out, you get about 130.2, which is what they say. And so this is what the in atomic mass units, that many atoms would weigh. And so 1 mole has a mass 130.2 grams. And so if you need a mole of this octanol, you would scoop out 130.2 grams of it, and that would give you a mole.